Okay. And all of combustion, we're talking about redox reactions today. So we're going to introduce that concept. And all of the combustion reactions are redox reactions. And so most of your explosions and so on are also redox reactions. So here, who is being very sophisticated. So let's go through the Alex reports. Okay, sticker time. I want to give stickers to the folks who at least started, right? It's not due till Monday, but they started already. So I've got this image on my phone of the people. So where are you? Cadence Robinson. All right, there you go. Hannah Klein. Ema, which one? Alicia, Alicia. Mia. Yeah. Start on. All right, so good job on getting started on those things. I want to do everything I can to get you to take small bites of the elephant because it's a lot of material. Tiny little glasses of water. This is like drinking out of a fire hose, and so you want to get it in small doses if you can. Okay, so these are the topics we're covering today. We're going to be able to get through all of these today and be ready for Monday. So we'll cover the whole thing that's due on Monday, and that's good because this just going straight from Alex to chemistry, we're missing a bit of the theory behind some things. And so on Monday, I'm going to extend these topics on redox reactions. We're going to learn how to balance redox reactions because they're a little more complicated than just balancing a regular equation, chemical equation. You know how some of the combustion ones, the oxygens, you end up with the 5 halves and you got to multiply everything by 2. That's sort of level 2 complication. Redox reactions can be level 3. So there's lots of things going on. And so we're going to do that on Monday. It's really not in Alex. It will be eventually, but it's just not in this group of Alex. But this is the time to introduce that material. So I'm going to go through oxidation numbers and reducing agents and oxidizing agents in today's lecture, get you ready for the Alex homework. Then Monday, we're going to extend those topics. This is everything that we do with batteries is this material. So on Monday, I'll also talk about batteries and how they work and corrosion and some things related to electrochemistry, because that's what we're doing right now with oxidation and reduction reactions. So vocab time. We've talked about precipitation reactions, and that's going from aqueous to solid. So we're using that AQ and aqueous and then solid to tell you that something's happened. We've also talked about dissolution. Okay, so a solid like sodium chloride dissolving and becoming aqueous cations and anions, so sodium cation and chloride anion. So that would be dissolution. We also say dissolved. When it dissolves, that's the process of dissolution. And that's the opposite of precipitation. And then we have the other 2 types of, like the combination reaction, where you have 2 molecules combining to form a third, and decomposition. We've talked about those 2 things. So these are not the same as precipitation and dissolution, because look at the state of matter, right? These are not going into solution or out of solution. They're just combining or decomposing. But then we're going to add 2 new ones to this. Yes? Yes?
I think the dissolution.
Rain? Oh, right. Okay. Rewire your brain. Yeah. Just to be thinking about that. Yeah. So you need to the brain needs to think about precipitation outside as condensation. Okay. But that concept of something falling out. So like you've got a sky and all of a sudden raindrops collect and fall out. If you pour silver nitrate and sodium chloride into a beaker together, the silver chloride will precipitate. So it's like a clear beaker, and then it falls out. Kind of like rain's falling out of the sky. This is falling out of the liquid and becoming a solid. So it's that process. It's the falling out that is actual precipitation. So the rain's falling out of the sky. The solid is falling out of the aqueous solution. So that's why they're probably given the same name. Excellent. That's pretty cool to sort of, I hadn't thought about that connection to rain being called precipitation, but yeah, it's the same process in terms of states of matter changing. Okay, so we have a new one now in our classification of reactions, and this is oxidation. So oxidation is loss of an electron. So in this case, we have electrons showing up in our reaction. So sodium solid is going to sodium cation, aqueous, and an electron. It's giving that electron to something, or that electron's going through a wire, which we'll see in a minute. That's how a battery works. Okay, but that's oxidation. It's loss of an electron. So sodium solid, as it goes past the arrow, has lost an electron. So that's what we're talking about. The sodium solid, the neutral element sodium, is losing an electron and becoming a sodium cation. Okay. Reduction is the opposite of that. Reduction is the gain of an electron or multiple electrons. Here we have acid protons in solution, and if we can somehow get electrons onto those cations, those hydrogen ions, they can make hydrogen gas. Okay, so this is a common one. This is reduction. So these hydrogen cations were reduced as they went past the arrow. So they gained an electron, so they were reduced, and they became hydrogen gas. So these are two new reaction types that we need to be thinking about: oxidation reactions and reduction reactions. And so this sodium says, I lost an electron. And I say, are you sure? And he says, yes, I'm positive. This is a meme too, but I went ahead and put it on this slide here. Okay, so this is how people remember this. Oil rig. OILRIG, oil rig. Oxidation is loss. And we're Texans, we remember oil rigs. Okay, so oxidation is loss, reduction is gain. So when we talk about loss or gain, we need to think about the electron. So oxidation is loss of an electron, reduction is gain of an electron. So that'll help you remember it. So look at the reactions. Look where the electron is. See over here, here's the arrow, and the electron's on the right side of the arrow. That means that was loss of an electron. Is when you go past the arrow, you lose an electron. How do I know the sodium lost the electron? Well, because it's not on the sodium anymore. The plus sign means they're separated. Okay. So when it went past the arrow, it lost an electron. So that's oxidation. And then here's the arrow. It's on the left side of the arrow for reduction. So these two got together. So that species here gained electrons when it went past the arrow. And so that's a reduction reaction. It's just that simple. Okay. Let me set something up here real quick. Okay. All right, so now in order to keep track of these redox reactions, we talk about oxidation numbers or oxidation state. And so the oxidation number or oxidation state is the charge assigned to a particular atom. Now it's pretty easy for those previous ones for sodium. Sodium by itself is just got a 0 oxidation state, but then when it loses an electron, it becomes a sodium plus, a sodium cation. And so it would be an oxidation number of 1, plus 1. So here, iron chloride is an ionic compound made up of iron 2 plus cation with an oxidation state of plus 2. So that's how we would write it out. We'd say its oxidation state is +2. It's the charge is what it is. It's the charge on that species. And then the chloride anions have an oxidation state of -1. Now we use this to kind of keep track of what species was oxidized and what species was reduced when they went past the arrow. So this is how we tell if there's a redox reaction, a reduction or oxidation reaction. They always happen in pairs because electrons don't like to be in solution. So the sodium can't give up an electron without a pair to give it to. So if you get sodium metal and chlorine gas together, they'll exchange electrons and make sodium chloride. But the sodium's not going to just pitch out an electron. It's going to have to, it's like the chloride is stealing the electron from the sodium. Okay. So metals or elements bonded to themselves, pure elements, they have oxidation states of 0. So whether it be like sodium, solid, I mean, it's solid sodium, so it's not really an atom of sodium, it's a chunk of sodium, and all of those elements have all their electrons. They're not stealing electrons from each other. There's no reason why one sodium would steal an electron from the other sodium because they have the same number of protons. So there's no differential force on those electrons. They're sharing them equally. Same with oxygen. Why would one oxygen steal an electron from the other? They both have the same number of protons. Chlorine, same thing. S8, that's actually the natural form of sulfur. It forms a ring structure with 8 sulfur atoms. So it's a molecular structure of 8 sulfur atoms. And again, it's going to have an oxidation state of 0. That's something that you have to know because we don't write them, like up there, Fe2+. Pretty simple. You see the 2+, that's the oxidation state. But you look at Cl2, there's no 0 written here. You just got to know that there's a 0. Okay. And then molecules and polyatomic ions can be a bit tricky. Okay, so this is where you have to actually start thinking. So we got to use some of our knowledge of the periodic table. Yes?
Well, so would like chloride too it won't have a charge then up there, wouldn't it?
Right. Now, if it does have a charge, then something has stolen or given it an extra electron.
Right.
Yeah. So, but if you just see Cl2, then you just know that's a 0. So both of those have an oxidation number of 0. Okay, so let's look at oxidation states of atoms in molecules and in ions. So pro tip, whenever you're trying to set these up or figure out what the charge is on these different ions, start with the group 6A and 7A atoms. So 6A, that would be the oxygen group, and really we're only going to be dealing with oxygen and sulfur, the top two. What's their preferred charge? Like if they were going to make an ionic compound, 2-, right? Now, if they're in a bigger molecule, you can just sort of put, assign a 2- to every one of those oxygens and every one of those sulfurs, okay, if they're in a bigger molecule. And then with the 7s, those are going to be -1, the fluorine, chlorine, bromine, iodine, okay? So when we look at this, let's assign the oxidation states for all the atoms in potassium nitrate. So notice the overall molecule, it's got a 0 charge up here, okay? So that's the whole thing. But the charge on potassium, what do you think it's going to be? Oh, wait, let's follow my rule. I said start with the group 6A and 7A atoms. And so we're going to say these oxygens are 2-, okay? And there's 3 of those. Okay, and the potassium over here, what do you think the potassium is? +1. Okay. And so the nitrogen here in the middle is the only one we're unsure about. So do you see what I'm saying? Let's do the oxygen first, let's do the potassium, and then let's figure out what the nitrogen is. Because we're assigning numbers, oxidation numbers, to every atom in the molecule. Okay, so we have a +1 and a -6. So +1 for here, +1 and the -6 equals 0. See this 0 right there. Okay, so +1, and I've got to have something else right here. So what does the nitrogen have to be? +5. Okay, so this is going to be a 5+ on the on the nitrogen. For some reason, when we write them on the elements, we put the 5 in front. So it's 5 positive charges. 1 positive charge for the potassium and 2 negative charges for each of the oxygen, and there's 3 of those. So those are the oxidation numbers for the potassium, the nitrogen, and the oxygen. Let's practice a whole bunch of these. Okay, here's mercury 1 sulfate. All right, so again, the whole thing is 0 charge. Let's write out, I'm going to erase this potassium stuff up above so I have some space. Okay. So I've got 4 oxygens, and there's a -2 for each of those. The whole molecule is 0 charge, so it has to all cancel out. Do y'all know what the mercury 1 is? It's Hg2 2+. Okay, so this whole thing is a 2+. It's 2 times a 1+, right? So 2 times a +1. And so we got to figure out what we got. We got a -8 here and a +2 here. So what does this sulfur have to be? +6, right? So +6, +2, so that's a +8 and a -8, that equals 0. So the sulfur is going to be a 6+, each oxygen is going to be a 2-, and each mercury is going to be a 1+, and there's 2 of those. So this is just like a little game trying to figure out what the charges are. And the way to get started is to start with those oxygens and the chlorines, or the group 7. Okay, here's dinitrogen tetroxide. The whole thing is a 0 charge, so we have to all add up to 0. So we've got 4 times a -2 for the oxygens. All right, so that right there is going to be a -8. And so this has to be a 2 times a +4, right? So we've got on each of these nitrogens a 4+, and on each of these oxygens a 2-. 2 times 4 is equal to 4 times 2, so that's good. Everybody see that? I do lots of examples because this, again, repetition is the mother of learning here. All right, this next one, carbon tetrabromide. So each of those bromines is a -1. The whole thing adds up to 0. There's 4 of those. And so we're going to have a 4+ on the carbon. So we have 4 plus 4 times a -1 equals 0. I feel like I'm going fast. Any questions? Okay.
So you just multiply it by the subscript.
Yeah, that's right. Whatever the charge is. So you start, like I said, the oxygens are -2, and so you just multiply those, that -2 times however many oxygens you have. All right, dichromate anion. This one's a little tricky because it doesn't add up to 0. It adds up to -2. Okay. So that 2- there on the dichromate is for the whole molecule, or it's polyatomic anion is what it is. Okay. So I have 7 times a -2. That's for the oxygens. So this piece right here is for the oxygen. So that's a -14, and it's got to add up to -2. So I can't cancel all 14 charges. How many charges do I have to cancel to have 2- left? 12. So I have to have 12 positives. Okay. So this is a 2 times something -14. Yeah, so 2 times 6. So each chromium is 6+. Did y'all ever watch that movie Erin Brockovich?
Yeah.
And she was talking about hexavalent chromium. That's what that is right there. So hexavalent chromium is a positively chromium that's got a plus 6 charge. So some of that was dumped in the water, and it was giving the kids cancer and so on. And that was the lawsuit against the environmental damage that was taking place by this company. So that's a pretty good movie to watch. Interesting show. Of course, Hollywood plays a little bit loose with the facts, but in general, the thing happened. It was about a real event. And so hexavalent chromium is a problem. And they're trying to move to their chromium plating processes to trivalent chromium. So it's less harmful. So. All right, let's do one more. Ammonium ion. So here's a polyatomic cation. That positive charge is the charge on the whole molecule, so that has to add up to a +1. So we're going to end up equaling a +1. And then there's 4 hydrogens. How many? So it's probably, each hydrogen's probably a +1. Okay. So we can't cancel all 4 of those positive charges. We only have to cancel 3 of them. So we need a minus what? -3. So nitrogen's a 3-. Each of the hydrogens would have an oxidation number of +1. That all adds up to the total cation charge of +1. So those are oxidation numbers or oxidation states. Now, if you have a molecule and you have an atom in a, like say this nitrogen in NH4, if you've got that 3+ nitrogen as a reactant, and then somehow you produce nitrogen gas, N2, now that nitrogen's charged to 0. So it went from a 3+ to 0. It can't do that if it doesn't get electrons. So if you're looking at a balanced chemical equation, or even an unbalanced one, and you're looking at the species on the left and the right, how do you know if electrons have changed place? Because you'll never see electrons in just the molecular formula. Like you won't see the electrons in the reaction. That's what's happening as they go past the arrow. They're changing electrons. So how do you detect when electrons have changed hands? You look at these oxidation numbers. And if the oxidation numbers have changed, like you go from NH4+ to N2, you know that nitrogen was a 3+ on the ammonium ion, and now it's a 0. It had to have gained electrons. And so that nitrogen was reduced as it went past because it gained electrons. So this is recognizing what was oxidized and reduced. So we can look at this. This is exactly what I was just talking about. We have a nitrogen gas going to NH3. And so we need to know, did the oxidation state of that nitrogen change? Yeah, absolutely it did. Okay. So this was a 0 here. This was a +3. No, -3, sorry. Okay, so there were some electrons that changed place. So yes, this was an oxidized, or this was a atom was reduced. It went from 0 to -3, and reduction is gain. Remember oil rig, reduction is gain. So it went from 0, and now it's negative. So it got more electrons. So it gained electrons. Oh, the next one. So let's do the scratch paper up here. So let's look at this carbonate. Okay. Na2CO3. So this is, each one of these sodiums is going to be +1. So there's 2 of those. And then this oxygen here is going to be 3 times a -2. So that's -6. And it's a neutral compound. All right. So we've got, so -6 here. And we got a +2 here. Okay, so this needs to be what? A +4. Yeah, +4. Okay, so this is a 4+ on the carbon and a 2- on each of the oxygens. All right, so then let's look over here at the CO2. Okay, we got 2 times a -2. equals 0. So this is a minus 4. And so this has got to be a 4 plus. So the carbon is the highlighted atom. And it was plus 4 on the left, plus 4 on the right. So we can look at that and say that highlighted atom was neither reduced nor oxidized because its oxidation state didn't change. It was plus 4 on both sides. So that's all you're doing for these kinds of Alex problems. You're just trying to first pick out make the oxidation number and then see if it changes as it goes past the arrow. If it doesn't change, then that particular atom was not oxidized or reduced. Okay, what about this next one? Oops, I already gave it away. This one, we don't even really have to do like the specific numbers. We can just look to see what the problem is showing. We know that carbon bonded to itself is 0. And now carbon's bonded to oxygen. Now, let me just tell you, the word oxidized and oxidation came from these oxygen reactions. And so if something goes from happy little carbon all by itself to now being attacked by oxygen, it was oxidized. That's where it came from. Oxygen came in and stole 2 electrons for every oxygen atom. And now it's been oxidized. It lost electrons. So oxidation is loss of electrons. So that's where the phrase comes from. Oxidation comes from reaction with oxygen, because oxygen is an oxidizing agent. It likes to take electrons. It's an electron thief. Okay, so it comes up and it'll steal electrons from metals and make them rust. Like iron, the oxidized iron is rust. So you have iron metal, happy as can be, 0 oxidation state. Here comes oxygen, stealing electrons from it, corroding it, making it metal cations. Down here, this one's easy as well. We're looking at Cl minus going to Cl0. Okay, so it was, let me go ahead and check that one. All right, so it went from -1 to 0. And so it had to have lost an electron, right? It went from -1 to 0. Electrons are negatively charged. So if it went from -1 to 0, then it lost an electron. And so that would be oxidized. Any questions on these? Notice how it builds. You got to know how to make your oxidation numbers first, and then you can answer these questions. Okay. Now, this one is a little more interesting because we have this idea of a reducing agent and an oxidizing agent. Okay, so we need to decide whether each chemical reaction in the table is an oxidation reduction reaction, because it may not be. If it is a redox reaction, write down the formula of the reducing agent and the oxidizing agent. So this word agent is important. Okay, so we're gonna learn that. That's really the vocabulary word associated with this problem. So let's look at this problem here. Notice how we have NO3 here and NO3 there. So the number of oxygens attached to the nitrogen did not change. So that's a clue that there was no oxidation or reduction going on. Okay. What about the water? So the water, H2O, it got a proton from the nitric acid. Okay, so it looks like there was a charge change, but that was a proton that came over. It wasn't an electron, changing hands or anything like that. So this is an acid-base reaction. Okay, so proton transfer is acid-base reactions, not redox. Redox is electron transfer. So we have proton transfer, which is acid-base. We have electron transfer, which is redox. So this one is not a redox reaction because none of the oxidation numbers have changed. Even this proton over here, it was a plus when it was attached to this nitrate ion, and it's a plus still when it's attached to the water. So this, we don't have to do anything with that one, just click no. Okay, but this is a combustion reaction, and combustion reactions are redox reactions. because the oxygen's coming in and it's oxidizing the carbon and oxidizing the hydrogen. So it's stealing electrons from everybody. So that's what's going on in combustion. So let's figure out what the reducing agent is and the oxidizing agent. Okay, so in combustion reactions, the reducing agent is the fuel and the oxidizing agent is oxygen. So how many people, well, y'all are young, you probably haven't bought a house, but a real estate agent helps you buy the house, right? They're the person doing things. So oxygen is the oxidizing agent, okay? It's doing the oxidation. The fuel was oxidized. This is where we get into grammar, okay? There's a past tense, there's all kinds of things. So the fuel was oxidized by the oxidizing agent. Does that make sense? Still, people get it mixed up. Okay. So that's one area where people get confused because they're just not paying attention to the grammar. And just listen to that statement. The fuel, in this case ethane, the fuel was oxidized by the oxidizing agent. And the reverse is also true, that oxygen was reduced by the reducing agent. So they exchange. Okay, so that's, if you get confused, go back to this part of the video and listen to me say that 4 times. Okay, so pro tip, oxygen's almost always an oxidizing agent. That's where the name oxidation comes from. We kind of talked about that. Okay, so let's break this in. This is a single replacement reaction here. Or no, these are combinations. So for each reaction in the table below, write the chemical formula of any reactants that will be oxidized, and the second column and so on, reduced. Okay. So what we're looking at is, let's do our oxidation numbers. So we have 0 on the left, 0 on the right, but then we get, for each of our reactants, and then we end up over here with an iodine minus and a copper plus. Okay. So notice what this says. This says oxidized. Okay, we're not talking about the oxidizing agent. We're talking about what was oxidized. So the reactants that were oxidized. So which one lost an electron? The copper or the iodine? Which one lost an electron? Yeah, so it went from 0 to positive. So that's where it lost an electron. Okay, so this first one would be copper. Okay. And then obviously then the next one would be I2. That would be the thing that gained the electrons. Okay. So reduction is gain. So when it was reduced, it gained electrons. Same thing over here, oxygen 0, zinc solid 0 to oxygen 2 plus, 2 minus. Goodness, don't look at that. 2 minus and zinc 2 plus. Okay, so the zinc was oxidized and the oxygen was reduced. And the last one, the nickel and the sulfur. So we end up with sulfide, which is 2 minus, and the nickel in this case would be 2 plus. So the nickel lost electrons and was oxidized, and the sulfur was reduced. So these reducing agents are kind of the victims, okay, and the oxidizing agents are the thieves. So thinking about the electrons, the oxygen, the sulfur, the iodine, they come in and they want to be negative. So they want electrons. So oxygen's the most common oxidizing agent, okay, because it's 20% of their atmosphere. So every material is in contact with an oxidizing atmosphere, and oxygen is attacking things. It's attacking all of our plastics, the tires on our vehicles. You used to set a trailer out behind the barn for, 5 years, you go and the tires are all cracked. That's because of oxygen. It's cracking those polymers and degrading it. The metal is rusting because, again, oxygen is an oxidizing agent, and it's stealing electrons from the metal and making them corrode.
So are the oxidized reactants are the reducing agents, and the reduced reactants are the oxidizing agents?
Yes, yeah, and it all comes down to the grammatical tense, right? The past tense. When we say these reactants were oxidized, that's past tense. So when they went past the arrow, that event happened, and we're talking about what happened in the past. These guys had their electrons stolen from them. Okay, by whom? By the oxidizing agents. These were oxidized by the oxidizing agents, and these guys were reduced by the reducing agents. Now, like I said, oxygen is the most common oxidizing agent, but these halogens are also bad too. If you have a swimming pool and you've got a chlorinating system or whatever, and that chlorine gas, if there's a leak and you go and look at it after a few days, all the iron-based metals around that thing are going to be completely rusted because that chlorine is going to really attack the metal. We were trying to do this in graduate school. We were going to get rich, okay? My buddy said, there's a lot of platinum on these catalytic converters. So we would go to the junkyard and we would dump the catalytic converter beads out of catalytic converters. And we were going to try to extract that platinum from those catalytic converter beads. It's ceramic beads coated in platinum. So we had to come up with a really strong acid mix. It's called aqua regia. Okay, it's nitric acid and hydrochloric acid all mixed together. It makes this red fuming liquid, and it will dissolve the platinum. Okay, but it also produces a lot of chlorine gas. We did this in his garage. We came back, we had our solution in the garage. It must not have been sealed very well, because then we came back into the garage the next week and all of his tools were rusted. Like there was just rust everywhere in his garage because of that chlorine gas. And so probably wasn't good to breathe either. So we did have about almost a pound of platinum. It was a lot. We had done this for several weeks, and we had even made a little makeshift hood. I'm sure it looked like a meth lab, but it wasn't a meth lab because it was all kinds of, it was a little plywood hood with a fan on the top, and we took the fumes out the basement window onto this plant he was trying to kill. And anyway, it was a great operation. But he was trying to boil down the solution to concentrate it and precipitate it out. And in our big flask was a pickle jar, and it busted, and all of that platinum went down into the concrete in his basement. Yeah, and so we're looking at this big gray puddle and all of that platinum in the concrete, and we're like, oh man. Anyway, it's a couple of months of work gone. So,
And the tools all messed up too.
yeah, that's right. Yeah, it's no good. So don't do it at home, right? Okay, so let's look at other parts of the redox reaction. Again, identifying reactants that were oxidized and the reactants that were reduced. So now we're dealing with single replacement reactions. Okay. So we had been doing reaction classification, and some of the ones on Alex, as you go through all the different ones, it said double replacement and single replacement, and we never saw any examples of single replacement, but these are examples of single replacement. So what's going on here? Notice it's iron by itself over here and copper bonded to chloride, and now they've changed places. So we've just replaced one atom. Okay, so that's what we mean by single replacement. It's just the metals, one becomes a cation, the other one becomes a solid. Okay, so this is iron 0 becoming iron 3+, and this is copper 2+ becoming copper 0. So which one of those went up in number? Which one lost electrons? The iron, very good. So this top one is going to be iron, and then whichever one was reduced, then it lost the reduction gained electrons, so it went down. So 2+ down to 0. Now when I looked at Alex, it was saying that it was copper chloride, but I was putting in copper 2+, because when you put copper chloride in solution, they break apart and you have copper 2 plus, and that was the actual thing that was reduced, not because the chloride didn't really change. It was just a CO minus the whole time. But I am happy I typed in the copper 2 plus as an answer, and Alex accepted it. So it has the correct answer and then the closely correct answer, copper chloride. So the next one, we're looking at zinc metal here, going from 0 to 2 plus. And here iron's going from 2 plus down to 0. Okay, so the zinc went from 0 to 2 plus, so it lost electrons. Oxidation is loss of electrons. So the zinc was oxidized, and then the iron sulfate was the species that was reduced, but it was really the iron 2 plus cation. Let's do it again for practice. Fe2 plus going down to 0. Magnesium 0 going up to 2 plus. So the magnesium lost electrons and the iron gained electrons. So I was happy. I would not include the anions on those, and so I was glad that Alex would count these as the right answers. Okay, so that's technically correct. Because the sulfate hasn't done anything. Sulfate wasn't reduced or oxidized, and neither was the chloride.
I guess the question is, you can put that like on a test.
Yeah, and it wouldn't be, it would never give you like both of these because they're both right. So, yeah. And I would give you these. These would be the answers that I would be looking for.
You wouldn't want us to like include the spectator.
Right, yeah, because they really are just spectators. They just start there. Yeah, they're just there to help it dissolve. Okay, now these are getting kind of fun. Okay, so the activity series. This question asks, predict whether this simple electrochemical reaction will happen and decide whether it happens in these situations. And you cannot do these problems without the activity series. So if you know you're doing this on Alex and you're like, how the heck am I supposed to answer this question? You need more data. So you go over here and click this little data button and you get this whole thing. And then down here at the bottom, it says metal activity series. So you click that and you get this activity series. So these are how active the metals are in terms of them donating electrons and wanting to be in solution. So the more active an element, the more it wants to be a cation in solution. Okay. It's related to how hard they push electrons. And so this will allow us to determine if a metal and a cation in solution will change places. So what we just did, the single replacement reaction. So we had a metal and we had a cation in solution, and they spontaneously switch places. The solution cation becomes a metal solid, and then the metal solid becomes a cation in solution. We can see this is called a silver tree. You take a copper wire and stick it in a silver nitrate, and this reaction takes place. The copper goes out of solution, goes out of the metal here, and the silver starts to plate out on the copper. So here the electrons are going to the silver, and the silver is plating out and sticking to the surface, and then the copper cations are going into solution. You see that the solution is turning blue. Can you see that color change? That's the copper going into solution. So copper cation in solution is blue. And then you see this fuzzy stuff showing up on the copper wire. That's the silver solid. Now, how would we predict this? We look at the activity series, and we see that copper is above silver. And so what this means is copper would rather be a cation than silver. So you put those two situations together. If you have silver solid and copper in solution as a cation, nothing happens. If you have silver solid, if you have a copper solid and silver in solution, that's upside down. So whatever's in solution, the top element on this chart wants to be in solution. The bottom element wants to be solid. So this is saying that if you have copper solid and silver in solution, they're going to swap places because copper's more active. Whatever's more active wants to be a cation. And it's related to how hard they push their electrons onto others. So what are our most powerful batteries right now? Like, what are they making these automobile batteries out of? Yeah, look where lithium is. It's the most active metal. It's pushing that electron off as hard as it can. And so it has the potential to give you the highest voltage in a reaction, okay? So let's use this. So we look at this, decide whether this reaction happens. And so we're looking at a strip of solid palladium metal put in a beaker of silver cations. It's silver nitrate, but we don't care about the nitrate. So it's the silver cations in solution and palladium metal. And so silver's in solution. Is it above palladium? Yes. So down here at the bottom, silver is already in solution. So we're looking at this pairing right here, silver and palladium. So nothing happens. There's no chemical reaction. So we just check no. We don't have to write anything as far as a chemical reaction. So I mean, I started this reaction here just to show you that it's silver cation, already aqueous, and that's what we would end up with. It would be palladium solid plus Ag aqueous, because silver wants to be aqueous, and that's going to force palladium to be solid, but they're already in that situation, so nothing happens in this reaction. So you wouldn't put any of this into Alex. You just click no and don't put anything. Okay, but the next question, they're switched. So notice this other one is solid silver put into a beaker of palladium ions. Okay, so silver is above palladium, and silver wants to be aqueous more than palladium. So they swap places. So yes, there's a chemical reaction, and this is what you would put in. Palladium cation plus silver solid equals palladium solid and silver cation. All right. Now they may, you know, if you get that wrong, Alex may be wanting to see the nitrate on there. Okay. Yeah, and so you would have a nitrate on both of those, and so that may be the situation for Alex. I have to check that. So that's how you use the activity series. Whichever one is on top wants to be the cation. If that one on top happens to be the solid metal, then they're going to switch places. And then here's just some points on the activity series. As a rule, whenever we're looking at these other kinds of reactions, these are more difficult. So let me just go all the way. We got 2 more minutes. We've got cesium plus water, and okay, that's, you know, where's water on this list? We have H2O. I mean, we have H2, but we don't have water. Okay. And so as a rule, only group 1A and 2A metals will produce hydrogen gas from water. Metals higher than H2 will produce H2 gas from acids. So cesium here, you see it's a group 1A, and so we know that it's going to produce hydrogen from water. So we know we have our reactants here. We know this is one of the products. And so we've just got to figure out what this other product is going to be. It's going to be a hydroxide of some sort. Okay. And so you just got to balance that reaction. Here's aluminum and HCl. So that's going, metals higher than H2, and here's aluminum up here. It's higher than H2, and so it's going to produce H2 from acid solutions. So aluminum plus HCl will produce hydrogen gas. And then you got to figure out what you know, how to balance it out. It's going to be aluminum 3 plus and Cl minus times 3. And so that's going to be the reaction of the aluminum and hydrochloric acid. And then we have aluminum plus water, no reaction, because aluminum is not group 1A or 2A. All right, so we'll finish up these last ones because they're pretty complicated. We'll finish those up on Monday. All right.